The recording will be available after the webinar. You would also be able to download the presentation in PDF format if you'd like to show it to your friends or colleagues. And with that, I would like to hand the word over to Chris.
Thanks, Max. Good morning, good afternoon, everybody. And as Max said, yes, we're here today to talk about server-side caching, and with a reference to a certain degree as an alternative to all flash arrays. If you could move on to the first slide, Max, thank you. So I'll just give you a bit of background about myself before we start. I've been in the IT industry about 27 years so far, covered pretty much everything from IBM mainframe through Windows and open systems. I currently work as a co-founder and consultant at a company called Lantern Blue, and we're based in the UK. However, outside of that, I do a little bit of blogging and on a site called Architecting IT. Now, if you want to follow me, you can follow me on the Twitter handles that are shown there. The one that's probably the most useful is the Chris M. Evans one, or you can find stuff that I do on the web. A couple of web references to that too. Okay, if you could move forward, Max, and we'll go through the agenda of what we're going to talk about today. So, over the course of this presentation, what you'll learn. First of all, we'll talk about the Pareto principle, or what a lot of us know as the 80-20 rule, and how that references to the data on our servers and our systems. We'll then talk about server-side caching and how it works, and we'll talk about some of the benefits and disadvantages of this technology. We'll then look at how we can implement this in a virtual environment and a non-virtual environment and see how there are differences between the two. We'll then briefly talk about some of the hardware products that we would use to implement server-side caching. And finally, we'll talk about a vendor roundup. And at that point, I'll hand over to Max, and Max will take you through some of the features of the StarWind product with reference to this. So first slide, please, Max. Next slide. Thank you. So let's talk about the Pareto principle. So this is a principle that was invented and named after an Italian economist called Vilfredo Pareto, and it's something that we probably are all quite familiar with, and it's the idea of the 80-20 rule. And that's pretty much summed up by the expression you can see there, where we say that roughly 80% of the effects of something come from 20% of the causes. And I put an example in there that is quite an interesting one, and that was Microsoft. They noted that if they fixed the top 20% of the most reported bugs, that actually fixed 80% of the problems in their system. So as you can see, we see this everywhere in our lives. We know that 80% of the traffic is is usually generated by 20% of the actual activity. And if we flip on to the next slide, Max, I'll give you an example in terms of the working set of a system. Now, this is a graph that's was taken from a live system, and it shows on the x-axis the data in terms of volumes, and on the y-axis it shows you the number of IOPS that were generated by each of those volumes. And what you see here is you see what is also called the long tail effect, where on the left-hand side of the graph, the number of volumes there are generating the majority of the I/O, and then the remainder are generating a very small percentage after that. And this is a very typical profile that we see on servers and on storage arrays, and that's that a small number of LUNs, or even within a LUN, a small amount of the data, generates the majority of the I/O. And that's quite an important factor when it comes to looking at how we implement something like caching. So if we flip on to the next slide, please, Max, we'll talk about why this is important and how this helps us with the idea of doing caching. So a good definition of caching is that caching describes the process, and I'll read it out because then we can talk about it after that. But caching describes the process of storing a copy of data on a fast storage medium such as DRAM or flash in order to improve the throughput or performance. The aim is to target this more expensive storage at only the subset of IO requests that need it. And this is something we call the working set. We pretty much see across the majority of environments that the working set of active data follows this Pareto principle, in that maybe 10 or 20% of the the data is active at any one time, and that generates the majority of the workload. And this fact allows us to implement caching, because what we do is we target the more expensive DRAM or flash at the data that needs it, and only the data that needs it. And if we look at how we would compare that to an all-flash array, clearly an all-flash array will put every piece of data on there, and potentially that's more expensive than we need to, more money than we need to spend in that scenario. So if we can move to the next slide, Max, that would be great, thank you. So to get into this into a bit further detail, well, what we're going to do is we're going to talk about the journey of an I/O. So in this instance, I've actually taken the stack of an I/O as it would be seen from a virtual machine, and how it goes all the way down to the storage. And the reason for showing this is to give you an idea of how I/O flows through a system, and how caching actually will help us as we go forward. So at the very top here, you can see we have the application I/O cache and the VM I/O cache. So within the actual VM itself, there will be buffers and queues that store an I/O request. Some of those are things like emulated SCSI devices, so the VM thinks it's talking to a real SCSI device. And sometimes we can emulate HBAs and network adapters. So from the VM itself, we see the start of the I/O. As we go into the hypervisor, and that's the middle three boxes there that are showing in that sort of slightly interesting green color, those three boxes indicate the I/O as it goes through the hypervisor storage stack. So clearly the hypervisor has to queue these I/Os up before it decides where it writes them. It might have to do some level of protocol conversion, because a SCSI request across the network might have to be written out on fiber channel. And of course, within that hardware of that hypervisor, the server itself, there'll be queues, things like the host bus adapter cache, and so on. Then we get on to the third section, and this is actually where we start hitting the external storage itself. So the first thing we go through is the storage network, and by this we mean switches, like fiber channel switches or network switches. We would then hit the array itself, and that array might have its own little cache of DRAM, and eventually, after we get through back-end SAS connectors, or however the disk drives in that device are connected, we get to some sort of permanent storage media at the actual disk where we store the data. This is also known as the backing store, and it's worth just mentioning that now, because as a term you'll hear and you'll see people reference something called the backing store. What we mean by that is the permanent residence for our data in this sort of environment. So as you can see, it's quite a complicated stack that we go through in order to get I/O. And this will become more important as we go through talking about how the caching process works. And we'll come back to that diagram in a few minutes. So before we get any further, let's talk about the process of caching and why there are different caching methods. So as we said earlier, the idea is to reduce the latency of our application by providing access to a faster storage medium, something like DRAM or flash. The idea is that DRAM or flash would sit in our server, and we'll see in a moment the hierarchy of that. But that hardware would sit in our server, and it would provide the I/O to the application rather than having to go to the backing store for that data. So what effectively we're doing is we're bypassing the need to go to the external storage array in certain circumstances. Typically, there are two types of caching that we do. So we do read caching, where a request might come in to read a block of data, and the cache provides it. Or we do three types of write caching, and you can see the three types of write caching on the screen at the moment. I'll go through these three types, and you'll see why they're important to understand the differences, because they apply to different types of data and they're used in different circumstances. So we can do something called write-through cache. Write-through cache, we actually take write data and we write it to the cache first, and then we write it to our backing store as well. And obviously this is the most secure way of doing it, because we know we've got a copy in the cache, and should the cache fail or we have a problem with it, we have a copy of that on our external storage. Once it's in the cache and we do that first write, there's a bit of a penalty for doing that first write, our subsequent reads then come from the cache itself, obviously until the data changes and we'd have to rewrite that block of data again. But effectively, we read the data from the cache back up to the host, and we write it through the cache as we write it out. Now, as we just said there, if you're doing a lot of write activity, you're writing it through the cache, and that might not be the most performance optimized solution. So another way to deal with write activity is to do something called write back. Now with write back, we write it to the cache, but we don't then subsequently write it to the external storage until sometime after in what's known as an asynchronous process. So we basically, we do that as a lazy write or a secondary task that does this afterwards. The immediate benefit here, and you'll see this on the screens and that we flip to in a moment, is that we can confirm that the write request is completed as soon as it's written to the cache, and that's much quicker than having to wait for it to be written to the external storage. So write-back caching gives us much faster accelerated writes, but of course we have to talk about some of the risks around that, and we'll discuss those later. Finally, there's a process called write-around cache. Now, if you imagine a scenario where we have many servers, and one of the types of data we're writing is sequential data, it would be very easy for large volumes of sequential writes to pollute our cache and to fill that cache up. And that's something that is no benefit to us because the chances are that data would not be reread. So to avoid that, we can use a feature called write-around. And write-around cache says, don't bother writing that data to the cache, but if it does need to be reread and I wanted to read it again, I can read it into the cache later. And that's a much more effective way for dealing with things like sequential data. So those typically are the three types of write caching methods, as well as obviously read caching. What we'll do is we'll just show that on a diagram, and we'll just use the diagram that we saw earlier. So as you can imagine here, we've got the same I/O stack. We've got the host writing data through the hypervisor into the storage network. Now in this scenario, what we're looking to do is we're looking to put a layer of caching software in our hypervisor and some very fast storage, which could be DRAM or it could be flash, and service some of those I/Os from that cache itself. With write through, you can see the process where in red we write the I/O to the disk, so we have to go through the caching software and write it to disk, but any reads can come back straight from the caching software itself. The red indicates the fact that we have to wait for that I/O to go all the way to the storage at the very bottom before we can tell the application that that write is complete. In the write back scenario, which is the middle of the three options, you can see that the red indicates that we write to the cache, but we can confirm immediately it hits there to the application. The green, which is the writing to the storage device, is done afterwards. So of course, that is our saving on that write process. We don't have to do that secondary level of write to the external storage. And that's where we see the savings with those two options. The third one, of course, is write-around. And write-around sees us writing directly to the storage array. So for a write request, we write the whole thing out. But when we come back in, we can read it back in, and then we can read it subsequently from the cache. And we see the most benefits from read caching there at that point. And these are the three main methods, and these are how we see the effect on our I/O profile when we actually use them. So let's go and talk about why this is actually useful to us, and why would we even do this in the first place? What are the benefits of caching? Well, from a technical perspective, there are three main benefits. Firstly, we can reduce the latency for our application, and we achieve that by putting the flash into the server and serving a large percentage of our I/O requests from that cache. The 80-20 rule really benefits us here because we know that the majority of our I/Os come from a small set of data, so by having a small amount of cache, we actually improve the performance of a large majority of our write requests. What we're eliminating here, of course, is writing through the hypervisor or the operating system to this external storage device. So effectively, we're eliminating many parts of what you might call the I/O stack. The second thing we see a benefit here, of course, is that we're reducing external I/O. So we're reducing I/O load on our external storage device. We're effectively eliminating those I/Os. So if you have a storage array that's quite busy, that's doing a lot of data in and out, and you want to actually reduce the load on that, caching actually helps that too. So you may see that you have an improvement on the performance of your external storage because it isn't loaded as heavily. Effectively, you're relieving it of a lot of the work it needs to do. And of course, the combination of those things effectively result in higher throughput for the application. Significant benefit obviously from reading the data from the cache instead of taking it from the external storage, but also from smoothing the I/O writes and producing a better overall throughput for our application. So that's all great from a technical perspective, and that's wonderful, but why would we do this financially? Why would we not just say, well, I'll just buy an all-flash array and I'll put all my data on an all-flash array? Well, of course, the benefit is cost avoidance. A combination of caching software, whether that's built into an application you use like StarWind, or whether that's a specific product that you would buy just for caching, the combination of that software and that flash or DRAM is almost always cheaper than buying an external flash array. And of course, if you know that your data isn't active across the whole spectrum, that only a small percentage of your data is active, you would be spending a lot of money buying an all-flash array when potentially you're not seeing the full benefit of that. The other cost avoidance benefit here is that you're extending the lifetime of your array because you're reducing that external I/O, and that may well save you the cost of acquisition or expanding that device itself. And that could be especially true if you're suffering a real problem with I/O, and you have to buy more disks or more flash within that storage array simply to get the I/O density. So it's all about cost avoidance. So let's move on and talk about some of the issues, because clearly, yes, cache sounds great, so why wouldn't we put all our data in cache, and why not use it for everything? Well, there are some disadvantages. The first thing we need to think about is something called cache effectiveness. Now, the cache is obviously not a copy of our entire data. It's actually a copy of the subset of data that's actually busy at any one time. And a cache may be 10% of our actual external capacity, or 20%, depending on how active our data is. The risk we have at any time with using a cache is that some of our data is not in the cache and we have to go to that external storage. As soon as we do that, our I/O response, whether that's a read or a write, more appropriately a read, as soon as we have to go to that external device, then we see a performance impact. And that might not be good for our application if our application needs predictable performance. So you have to be very careful with caching software in that instance, because if unpredictability is a big deal for you, then caching may cause you a problem. Now, cache software itself uses a number of different techniques. We call them algorithms, and they're used to either store or predict what data should be in the cache. Clearly, as data changes and things become more active, we have to eject some data at the cache and replace it by other data. And we see techniques like least recently used, where we throw away the block of data that was the last to be accessed. Those sort of algorithms get used by cache software. Some cache software tries to be a bit more intelligent than that and will look to identify data they think might need to be brought into cache before it's actually requested. So they'll pre-fetch data. And by doing that, those sort of pieces of software can potentially increase cache effectiveness to a very high level. And that's something we want to make sure we can achieve. But we always have to bear in mind that there will occasionally be data that's not in our cache. And we might see a problem with the response time because of that. The next thing to consider is data integrity. So if we have data in our cache and our server fails, then that isn't a problem if we're only using the cache for reading, because we know we've got a copy of that on the shared storage array, the backing store somewhere else. However, if we decide to use cache in write-back mode, where the current copy of data may only be in the cache and has not yet been written to the external storage, then a failure of that server or that cache itself could cause us to lose data, and that could be quite catastrophic, because clearly that data might be the blocks that are needed to keep an entire file system consistent. The answer to that is to duplicate that write elsewhere, and what we see people doing is we see people building, say, a cluster, especially things like VMware or Hyper-V, and they'll replicate the write to another cluster member in order to ensure that the data is protected in case of one of the servers failing. And that's our mitigation for getting around that sort of a problem. We have to be very careful, obviously, with write-back mode, because that is always our risk. And we might see that going forward mitigated to a certain extent as we see technologies like NVRAM come along, which could actually keep our data consistent across a reboot. The next problem we have is something called data concurrency. Now, if you imagine, again, in a cluster environment, we have one node that reads or writes the data. It could be very easy for one node to have a copy of that data that's inconsistent with another. And that could occur, for example, where one node writes the data to the cache and then writes that data to the backing store. The other node may have a copy of the data in its own cache, and that copy of that data would now be incorrect. It would now be out of date, and that needs to be fixed. So data concurrency has to be thought of, especially in clustered environments, to make sure that the software you're using for caching is able to cope with that scenario and is able to make sure that any of those sort of writes are replicated between the different nodes. The chances are, if you have the software that's fixing the data integrity issue, then it also fixes the data concurrency issue. And finally, one of the problems we've highlighted here is the idea of cache warm-up. We started this presentation by talking about how cache is read from disk into the backing store into the cache, and that first write, especially on a read request, would obviously be at the speed of the external storage. In order for the cache to become effective, we need to preload that or get all of that data into the cache, so then subsequent requests can be served from the cache itself. And obviously that's the point where we start seeing the I/O benefit. This process of loading data into the cache or getting the data into the cache for the first time is called cache warm-up. And initially, as blocks are loaded into the cache, we can see an issue with slow performance. For example, in a newly booted system where the cache is not persistent across reboots. We have to be aware of that, but then again, there are systems that could preload that data into the cache for us, especially if we know the sort of data we need to have in there. But we just need to be aware of the cache warm scenario too. So, we've talked about caching, we've talked about the process, we've talked about how it works, but we need to start getting into some real detail here and say, where would we actually do this cache process? And actually, to be frank, we can do it in many places across the infrastructure. What we've done here is we've highlighted probably 4 of the most common places we can do caching. We could do it directly in the application. So, and I've picked a couple of examples here of databases like SQL Server and SAP HANA. The latest releases of SQL Server are very much more driven to using system memory, increasing the volume of system memory in order to cache a lot more data. And obviously that's very, very practical for read data in a database environment. But there are solutions that can cater for data that's updated too. So we could put it in the application, and that's a perfectly acceptable way to do that. Our second option could be to actually put it into the operating system. The operating system already buffers data as it goes in and out of the system to external disk. There's no reason to say we couldn't put another layer in there of caching software which allows us to track and cache data more effectively. The operating system itself clearly is doing that, and there may be options to add more cache to the operating system directly, or it may be a product that we install to do this process. The third place we can do that is in the hypervisor, and you'll see that we've mentioned two scenarios here that you can do this. You can either do it as a VM, a virtual machine, or you could insert this as something that sits in the hypervisor kernel, i.e. as part of the operating system. We'll come on and discuss this in more detail because it's quite an interesting area of a solution, but one of the things that's just worth mentioning here is that as a VM, we see this being used as a technique to develop hyperconverged solutions, because we can distribute VMs across a hypervisor cluster and use it to create a virtual storage layer, and that's something that, for instance, the StarWind product can do. Finally, in terms of our hierarchy, we could do this in the HBA. And there are solutions, for example, from QLogic where an HBA can be paired with another HBA which has got flash on it, like a PCIe SSD card, and the HBA can be used to do the caching at a hardware level. This is quite an interesting solution, actually, because if you imagine the HBA seeing all of the I/O, whether it's coming from a hypervisor, an operating system, an application, it sees everything that goes through to that external storage. So in some respects, this is quite a clever way of caching. The one thing you have to be careful here, of course, is that we talked on the previous page about data concurrency and so on, and you'd have to make sure that those solutions support that directly, and they'd have to have some way, the HBAs that is, of communicating with each other, and they'd have to work in a multi-protocol environment, and sure enough the QLogic products do. So we'll go into a bit more detail now, and we'll talk specifically about how we implement caching in certain scenarios. So let's talk about non-hypervisor caching. Let's talk about how we would do this in an operating system like Linux, for example. What we've shown here is what might be a typical setup in terms of the layers you'd expect in the server. So we have our application layer, we have our virtual sort of data layer, so the application thinks it sees a file system of some sort, and then between there and obviously the ability to write this data out to disk, we would insert the cache software perhaps as a device driver. So it emulates an internal virtual device the host sees, or perhaps we put it in as part of the volume manager. And the volume manager would be in an ideal place to be seeing the data that's coming in and out from the external storage. We can put it in either of those two places. This sort of scenario typically would require an outage to install, potentially. And obviously, as you can imagine, the drivers and the whole and the volume manager amendments would be very operating system dependent and very version specific dependent. And because of that, obviously, if we ever upgraded the operating system, there may be upgrades to the cache software that we'd have to take into consideration at the same time. So if we move on to the next slide, we can talk about hypervisor caching. And hypervisor caching we can do, as we've mentioned already, in two methods. So we could install our software either within the kernel, and we'll talk about both of these separately. So we'll talk about the kernel first, kernel mode of operation. So here we insert the caching software as a device driver, for example, within the kernel of the hypervisor. And that means every I/O that goes to the external storage would come from the application, go through the kernel, and be written out to external storage. This is very tightly integrated with the operating system, very similar to the previous model, because effectively the hypervisor is an operating system, and therefore there would be very close dependence between the two. Theoretically, this would appear to be a nice lightweight solution, maybe not a massive amount of overhead in terms of additional performance and so on. However, in the implementations as they exist today, the overhead of the device driver may not always be obvious, and that's something that needs to be considered. Similarly, to install and remove the software may well require an outage, although that's not necessarily always the case. How about as a VM? Let's look at the scenario of doing this as a virtual machine. So when we say running the storage as a virtual machine, or the caching as a virtual machine, what we mean is we deploy a virtual appliance that also runs on the hypervisor. So the virtual appliance talks to the external storage, but it also presents storage to the hypervisor environment itself. That could either be through NFS, or it could be through iSCSI. But as far as the hypervisor is concerned, it is seeing some sort of storage platform. Now, when the application within all the other VMs on this environment writes data, the data goes through the virtual appliance, which caches it, and then it writes to the external storage, or or it reads from the external storage as required. This obviously is quite an interesting way of doing it, because the actual service can be deployed quite easily. We just simply install a VM and we redirect the I/O traffic. It means that potentially the virtual appliance is less dependent on the hypervisor version, and potentially there's no reason to say we couldn't cross share this between different versions of hypervisors if that's what we really wanted to do. Resource consumption is more transparent because we can measure what the virtual appliance is actually using, so it's pretty easy to see what the overhead of using this solution is. However, we have to bear in mind that we're now going through potentially more paths to get our data out, and having to traverse through the VM could result in higher latency times. Although that's not always the case, that is potentially a risk. So there are pros and cons to both solutions, and we have to really sort of decide what we think is the most appropriate for ourselves in that instance. So let's move on and talk about some of the hardware that sits behind this, because this is quite an important thing to get right. We clearly talked about and explained that a lot of the features are built into the software for caching, but clearly the data must be kept somewhere, and there are three possible ways we could do this. We could keep our local cache data in DRAM, which would be the fastest way of doing it, but of course that's not persistent. We could lose that data if we powered off the machine, and we'd need to put protection in there to cover that. But DRAM can be down into the nanosecond performance time, so having a product that can support DRAM is really quite a good thing, even if it's only for read caching. We could use something called NV DIMMs, which are a new form of DIMMs that are coming out, where flash has been added to that form factor, and they can be installed in servers and the data is persistent. Unfortunately, these are new devices, so we haven't seen many servers supporting them, but they potentially could be a very good way of doing caching. And finally, we could just put flash devices in there. We could put in PCIe SSD flash, or we could just put SSD drives in. And the one we choose is likely to be variant on price and capacity. One thing we will just go on to talk to on the next slide, if we just move to the next one, is a small consideration we must make when we're looking at flash devices. And that is the idea of endurance. So as I would imagine most people know, flash devices have a finite lifetime. They will they can only be written to a certain number of times before they wear out. And that measurement, that endurance, is known and is measured in a terminology called DWPD, or device writes per day. Now, I've just picked out a few products from, I think this is Samsung's webpage. It gives you an idea of a few of their existing products. And you can see here that with random workload, the variance could be 3 device writes per day, or as high as 25 device writes per day. So clearly the 25 DWPD device is much more resilient. It would last you a lot longer with write workload. The 3 product would not be very good at all, and in actual fact, if you look at the second line from the bottom, the Optimus Max SSD, which is a large capacity device, would be terrible to be used as a cache, because you can only write half the capacity of that on a daily basis. So that could actually wear out very quickly. So when you're looking for the hardware piece to put into your caching solution, you have to be very careful about the hardware products you choose, because they are very different. So let's just now talk about some questions to consider when we're looking at choosing a different product, and then we'll very quickly run through some vendor products to finish. So what should you consider when you're looking for the right caching product? Well, first of all, clearly it's obvious you can put cache into virtualization solutions like Hyper-V and VMware. So you should ask, do I really need it in there? Does it need to be integrated as part of that? Does it need to be integrated right into the hypervisor, or can I run it as a VM? You know, am I really that bothered about whether it's fully integrated? That question ties into the next question, and that is, do I need to do things like support replication, snapshots, and backup? Clearly, if some of my data sits in the cache and some of my data is sitting on the external storage, and I'm using some sort of snapshot technology, I might be snapshotting at the array level and finding I'm not taking all of my data because it hasn't been flushed from the caching product. So we need to be very aware that caching needs to support some of the other functions and features that sit around storage management. Am I working in a clustered environment? Do I need support for clustered configurations? Obviously, we see the reasons why that's important. We've talked about that already. And of course, what are my workload types? So if I have an environment where I know I've got large amounts of sequential workload, I may want a product that I know can exclude that and can do right around caching. And if I haven't got that, then it may cause me a problem for my solution. So let's talk about some of the vendor products out there and have a quick roundup of some of the options. So from the operating system perspective, we know there are products out there like StarWind Software's Virtual SAN, and I'm going to let Max talk about that in a moment. Hitachi Global Storage Technologies has two products, one called Server Cache, one called Cluster Cache. Server Cache can use DRAM for read-only caching and solid-state disks and runs across typically all of your standard operating systems. Cluster Cache is a bit more advanced and it actually integrates into some other technology that came from their acquisition of Virident. In terms of putting things into the hypervisor, at a VM level, I could use technology like Atlantis Computing's USX or ILIO, and they're memory-based caching, which allow you to speed up virtual machines and desktop solutions. The benefit of a product like that is it will actually deduplicate the data that's in the cache. So when you're running something like VDI, you'll see a very efficient usage of cache compared to some of the products because of that deduplication ratio. There's also Infinio Accelerator, which does caching based on NFS data stores, and that also does deduplication, but that's on your read-only product. So let's flip to the last slide, and then let's look at some of the other options, the hypervisor, kernel-based, and some of the one cross-platform. So from a kernel perspective, products we can install into a kernel, we have FVP from Pernix Data, which is possibly quite a well-known solution, recently upgraded to support DRAM and flash, and does write back and write through. vSphere itself has a feature built in called Flash Read Cache, but that's quite, clunky is not the right word, but it's not as flexible as it could be. You have to assign chunks of cache to each VM's VMDK, so it's a bit somewhat inflexible compared to some of the other models. VMware themselves invented something called Virtual SAN, which is a distributed storage layer, and that can do caching based on SSDs. And finally, there's a product called AutoCache from Proximal Data, which again is another hypervisor-based solution. One last mention there we should just give to SanDisk. They have a product called FlashSoft, and that fits both virtual environments and Windows and Linux operating systems. So as you can see, lots of products out there and lots of questions to ask those vendors. So with that, I'll pass over now to Max, and I think Max is now going to take you through the StarWind platform.
Right. Thanks, Chris, for an excellent presentation. And let me just switch over. So, quick overview. Who am I? So I talk about StarWind and caching here. So I'm currently StarWind Virtual SAN Product Manager. I've been working for this company for more than 8 years. So I know a little about this product and a little about the industry. And I've got more than 10 years of professional IT experience, mostly storage related. You can also hear my voice and see my face on StarWind events because I often participate in our exhibitions, and I'm the host of StarWind webinar series. Now, so the idea behind server-side cache is to simplify our I/O path. As Chris told, we want our cache to be close to our applications, and StarWind's idea is exactly that. We don't need to go a long path like you see on the left with HBA transmitting your I/O to storage network, then to the storage array where it is eventually cached, because it looks like the maze on the center of the screen. Instead, we just bypass it and write directly into the application host's cache. So be it a virtual machine server or just an application server, it uses local RAM as caching, and it doesn't need to go all that long way for submitting I/O to cache and eventually to disk. Now, there are some precautions for using cache safely. like Chris said, there are multiple ways of caching your data, and depending on the way you want to cache it, you get different caveats. Your mileage may vary and stuff like that. So there are three main principles. First one, the easiest way to go is to use non-volatile caching. So we use battery protected caching like you already do in most of the RAID arrays you have in your servers. Then you can use SSD caching, which is safe enough, because if your server fails, the data is not lost. And that's the way to do it with Flash. Then bit more interesting way to do your caching is to distribute between your application servers. Let's say you run a cluster and you have part of the cache on one node, part of the cache on the other node. So you can actually play around with that to get more performance and still benefit from the caching. But the ultimate idea is to keep your cache, so all of your cache, synchronized between the servers for real cache fault tolerance. So remember Chris told you about DRAM being the fastest cache available, but also the most risky one, because if you use it in write-back mode, you lose the server, you lose the cache data. If you have big cache, let's say 2 gigabytes, 4 gigabytes, that means that you just lost 2 to 4 gigabytes of your most recent data. That increases your recovery point objective and possibly corrupts the data beyond repair. So that's not a really good thing to do, and that's why we at StarWind provided a solution to deal with that. So the idea is to mirror the cache between multiple servers. So on this diagram here we have a basic reference architecture of StarWind Virtual SAN solution. So the idea of caching I/O locally is implemented on one server, and then as we add the second server, we make sure that all I/O we write on our disks get cached and also synchronized between the servers. So you only confirm the data when it is cached on both sides, not on just one side and in the storage. So this way we can use write-back cache and maintain it fault tolerant. So even if one server fails unexpectedly, you don't need to power it off softly, you can just toss the power cable out. The second server will have the same data in the cache no matter what. And of course the second server will flush that data to the disk immediately to make sure that if you toss the second power cable you don't lose your data. But even if that happens, you can add more servers for more resiliency and more redundancy in your environment. And the basic idea behind this software was to create a virtual SAN, a software which would virtualize your storage, or if we talk in BOS terms, use these days, provide software-defined storage. So just use local server storage and turn it into something more resilient, more feature-rich, and something much faster than just local storage. And then provide it to the upper-level applications or virtual machines. Now, the good thing about StarWind's cache solution is not only that it provides cache fault tolerance with minimum number of servers required, it also utilizes cache deduplication. So the data you write is first cached, is then deduplicated, and only then it's transferred to the actual disk. So this means you actually do less I/O to the disk and more I/O goes to the cache, like Chris mentioned with the Atlantis in-memory solution. You get the same approach with StarWind. And of course, writing less to the disk and combining our caching solution with StarWind LSFS or log structured file system underneath allows us to use high-capacity SATA spindles for primary production workloads, which has previously not quite popular in the virtualization world. Now, you may be wondering, what are the additional features StarWind has to offer other than provide you cache redundancy and cache deduplication, which is already something. The overview of our feature set is described in these 6 bullet points. So first of all, StarWind is not just a caching solution. It is actually a full-featured virtual SAN which has 0 hardware footprint. So effectively you just install it over your application servers, virtualize your storage, and start enjoying the performance boosts, the resilience you got by implementing virtual SAN solution, and you don't really need any additional hardware or software to be installed. So it's just StarWind to add that functionality to your existing environment. Then the cache and storage fault tolerance are delivered with just 2 servers. So most of the solutions doing the same type of storage virtualization require at least 3 servers, and all these servers have to be equally configured, and all these servers need additional equipment like 10 gigabit switching. In case of StarWind, you just use 2 servers, connect them with direct 1 gigabit or 10 gigabit cable, so no switch necessary, and let it work. One more thing is that StarWind is completely hypervisor agnostic, so you can install it on Hyper-V, on vSphere, maybe as a hypervisor, your choice, either as native application or as an appliance, and it will work, as we have designed it not to tie to a particular platform, but give people the ability to move freely and give them the flexibility they need in the virtualization environment. Of course, with the deduplication solutions I mentioned earlier, StarWind provides an interesting way of being flash friendly. If we use flash as our underlying storage, let's say we still have some all-flash LUNs shared by StarWind and you want some of the applications to reside on flash, StarWind deduplicates the I/O in the RAM layer and then it writes last to flash and it reads from flash, not only writes to it like it would be if you just use flash with no caching. So it effectively creates some sort of a barrier between your flash and your application, and your application's I/O doesn't always get all the way down and burn the cell on the flash array. This is quite useful for scenarios like VDI, where you have your underlying fast storage, then you have your big cache. Let's say you have the cache almost the size of your VDI. So effectively, all your writes are getting deduplicated in memory, and most of the reads also happen in memory. So flash remains untouched some of the time, and you effectively get memory computing speeds with that solution. And of course, the solution starts with 2 servers, but it can also scale up and out along with your application requirements. Let's say you want to grow your virtualization environment to 3 hosts, StarWind easily supports that. You want to add more capacity or horsepower to individual servers, StarWind also supports that. These things can be done with no I/O interruption and no flash interruption as well. So your caching is not turned off when you turn one of the scale-out groups servers and add additional resources to it. And of course you don't lose the caching when you resynchronize everything when adding a new server to your server farm. And last thing would be tiering the data, but not only within the primary storage array, but also offloading the cold data off the server to a dedicated snapshot storage. So let's say you have your 2 production servers running SAS RAID 10s with flash L2 caching and RAM L1 caching. You have some space left on it, but that space really costs money. So keeping cold data on that array, by cold data we usually mean snapshots, backups, any data which is not frequently used, keeping it on the primary production servers may not be the best idea from the cost standpoint. So StarWind allows you to offload that cold data to a dedicated server or to a dedicated array comprised of cost-effective disks easily and automatically. Should you need to restore from those snapshots, you can just pull them back on the primary system and spin off your production environment from that snapshot. And with that, I'd like to thank everyone for attending our today's event, and we get down to our questions and answers session. So let me just read out some questions we have from our attendees. Okay, a question from Ilya Surkov. Hypervisor caching ideal for VDI? Indeed, I would say so. So Chris, what do you think about hypervisor caching and VDI?
Yeah, absolutely. So bear in mind that VDI will be deploying multiple images of the same desktop. So you've got many images of that desktop out there, and obviously some potential benefit from possibly consistent and a similar sort of data, but mainly from the desktop. So yeah, caching would be very useful, and this is something that the Atlantis Ilio platform specifically targets. So it does deduplication of that data. So VDI works very well with caching solutions.
Thank you. I would also add that StarWind supports that too, as I mentioned on the previous slides. And here a question from Mr. Code Camely. Does the performance increase linearly based on CPU performance and core count due to deduplication and LSFS on StarWind hosts? I think I'll handle this one. The performance does not increase linearly. The graph is a bit more complicated, and usually it has to be calculated based on the working set and of course based on the amount of IOPS your solution needs to deliver. So there is no rule of thumb to tell that exactly. Then, and question from Arturo Cruz Torres. How much RAM is recommended for caching? Yeah, again, we do have a rule of thumb that we recommend at least 1 GB of cache per terabyte of storage, but depending on the working set, you may get away with less. Let's say your production environment is not so IO intensive, and in VDI scenarios, the minimum recommended amount of RAM equals the size, either your golden image or the size of your VDI, plus additional overhead to keep the non-deduplicated actively used data in memory as well.
So just add one little bit to that, Max.
Sure.
Clearly, everybody's data can potentially be different. You may have some active data, you may have less active data. It's very difficult to give an exact rule of thumb. What I would say is that if you look at a lot of the products that are out, and I'm sure yours is the same, the vendor products will give you an idea of how much data is being cached, how active the cache is, how much under pressure the cache is, so you can actually see whether you've got a solution that's underutilizing or trying to overutilize the cache. So it's important that you need to make sure that if you're buying a very specific cache product, that it does have some sort of interface that allows you to see how well the cache is being used and what the benefits have been.
Right, exactly. That's a really good point. And we got one more question. It seems in later versions, cluster storage in StarWind can have RAM cache adjusted in defaults to 128 megs. Is it dynamically using StarWind, one moment, scrolling down, using StarWind host memory? If so, what are the upper limits? So as of now, the cluster devices use 128 megs, and that was preset because the cluster entity is a new thing we develop. But if you create the devices the old way, when you go to host directly and then create a replication partner. In this case, you can set up any size you want, and there are definitely no upper limits. We currently test StarWind in an environment with 2 terabytes of RAM, and it easily uses most of that memory for caching. All right. I would like to thank everyone for attending our today's event. Chris, thank you so much for an excellent presentation. And please feel free to download our 30-day trial. You've got the link on the screen right now. And should you have any additional questions or any technical questions which may not be short enough for the webinar, feel free to drop us an email to sales@starwind.com or to info@starwind.com. Thank you so much and have a great day. Bye-bye.